We are now looking at the area of a parametric surface, where S is a smooth parametric surface given by this vector valued function R in terms of u and v. This is defined over an open region D, that's your domain, in the UV plane. Each point on the surface corresponds to exactly one point in the domain. Then the surface area is given by this double integral S, D capital S. Now, since our surface is given in terms of R in terms of u and v, this surface integral, this S, is the surface, D capital S is your differential surface area, is equal to a double integral where D is the region in the domain of the magnitude of the cross product of RU with RV times differential area A. Again, those RU and RV, those are your partial derivatives of R with respect to U and R with respect to V. So the surface area, if you have R in terms of X and Y, the cross product of R sub X with R sub Y, the partial of R with respect to X and the partial of R with respect to Y, is equal to this double integral where R is the region, equals the square root of 1 plus those partial derivatives squared, added together, differential A. Now we've seen this integral before, so this is directly related to that, but we're extending this to surfaces, parametric surfaces R in terms of U and V. In this example, we want to find the surface area of the unit sphere given by R in terms of U and V equals sine U cosine VI plus sine U sine VJ plus cosine UK, where the domain D is given where U is between 0 and pi and V is between 0 and 2 pi. By calculating those partial derivatives R in terms of U, R with respect to U and R with respect to V, we get the following. Treating U as a variable and V as a constant, the derivative of sine U cosine V is cosine U cosine VI. The derivative of sine U sine V is cosine U sine Vj, and the derivative of cosine U is negative sine U k. Take the partial of this R with respect to V, treating V as a variable. We get R sub V, or the partial of R with respect to V, equals negative sine U sine VI plus sine U cosine Vj plus 0k. Now we want to find the cross product of those and set it up using a matrix. And by multiplying across, we get the cross product is sine squared U cosine VI plus sine squared U sine Vj plus sine U cosine U. Our next step is to find the magnitude of that cross product. We're going to take the square root of each of these components squared, add it together. And it looks a little complicated here, but it does end up simplifying to just sine squared U, which ends up being sine U. Okay, so there's a little bit of algebra involved here and simplifying, but you do break it down to just sine U. Alright, so the cross product of RU with RV is equal to this quantity, and when you take the magnitude of that vector, you get, it simplifies to sine U. So when we calculate the integral for this surface area, it's going to be the integral, double integral, where D is the domain of the magnitude of the RU with RV cross product, dA, and we know that simplifies to just sine U. And differential area is going to be du times dv, where u, the bounds for u go from 0 to pi, and the bounds for v go from 0 to 2 pi. When we evaluate the inside integral, that simplifies to 2, and then when we evaluate the outside integral, we get our final answer of 4 pi. So that's going to be the surface area of the sphere, that unit sphere, given by that parametric vector valued function. Okay, for this example, I want you to find the surface area of the parametric surface R in terms of u and v equals 4u cosine vi plus 4u sine vj plus u squared k, where the domain D is given by u is between 0 and 2 and v is between 0 and 2 pi. Pause the video, try this one on your own, and then come back and check your solution. Okay, let's begin by taking the partial derivative of r with respect to u. And I'm going to switch to the angle bracket notation here instead of using the unit vectors I, j, and k. It just simplifies what I'm writing here. So if we take the partial derivative of r with respect to u, treating u as a variable and v as a constant, that derivative is going to be 4 cosine v. The derivative of 4u sine v, treating u as a variable, v as a constant, is going to be 4 sine v. And the derivative of u squared is going to be 2u. That's our partial derivative of r with respect to u. Now let's find the partial derivative of r with respect to v. We're treating v as a variable here and u as a constant. So the derivative of 4u cosine v is negative 4u sine v. The derivative of 4u sine v is 4u cosine v. And the derivative of u squared is equal to 0. We're treating u as a constant there. Now we want to find the cross product, ru cross with rv. You can use that cover-up method or write it as a matrix. When you cover up the first column here and multiply here and here, actually, if we multiply 4 sine v times 0, you get 0. 2u times 4u cosine v, and subtract that, you get negative 8u squared cosine v. Now cover up that middle column here, multiply across here to get 0, multiply across here to get negative 8u squared sine v. And then finally cover up that last column, multiply across here and here to get 16u cosine squared v plus 16u sine squared v. Now if you factor out the 16u here and the 16u here, you'll be left with cosine squared v plus sine squared v, and we know that that's an identity, so this is going to simplify to the following. Negative 8u squared cosine v is the first component, negative 8u squared sine v is the second component, and 16u, when you factor that out, you're left with cosine squared v plus sine squared v is equal to 1. So that's going to be your ru crossed with rv. Now the surface area formula is setting up a double integral where you take the magnitude of that ru crossed with rv. So let's do that next. Scoot that down. Alright, so the magnitude of ru crossed with rv is the square root of, we're going to square each of these components to get 64u to the fourth cosine squared v plus 64u to the fourth sine squared v plus 16 squared is 256u squared. Now here again we can see that we have a cosine squared v and a sine squared v, so if we factor out the 64u squared from both of those terms, we can then simplify this to the square root of 64u to the fourth. We factor that out of both of those and we left with 1 plus 256u squared. Now this one you can further simplify by factoring out a 64u squared from both of these. And you get u squared plus 4. And then if you take the square root of the first term, that's going to be 8u times the square root of u squared plus 4. So that does simplify to this. Now we can then set up our integral here. Now what I want to do actually before I set up the integral, it would be nice to determine the order of the differentials for dA as well as the bounds of integration. We're given the intervals for u and v. You can think of this as the u-axis is the horizontal axis, the v-axis where u goes from 0 to 2 and v goes from 0 to 2 pi. The region is right here. It's vertically simple, horizontally simple, so it really doesn't matter what order. So we may end up deciding that it would be better if the order of the differentials was dv du because of what this integral is going to look like. So our surface area is going to be the double integral of this magnitude is 8u times the square root of u squared plus 4. Now our differential area here is either going to be du times dv or dv times du. So we can make it dv times du. So their bounds for v are going to be the inside bounds from 0 to 2 pi, and our bounds for u would be the outside bounds from 0 to 2. You can work out this double integral to get the solution, which is approximately 245.085. So that would be the surface area of this parametric surface given the domain listed.